Hi, everybody. I hope you're listening to this tonight. We're going to start today with a review of where we've been. And I thought, in honor of, I have nothing in honor of because I thought I would do problems involving garden gnomes. So let's take a look at garden gnomes today. Um, population in my garden, population of gnomes in my garden grows exponentially. The initial population was 7 garden gnomes. After 3 years, I was up to 12 garden gnomes. Okay, first I'm going to ask, what is the growth rate of the gnome population? I need to know my R. Well, we've done a lot of these problems now, and this kind of reminds me of the Tucson problem, where I gave you 2 data points and including an initial amount. And so we can start with P equals P sub O e to the RT and plug in what we know. We know the original amount is 7 e to the RT. And then I can plug in this ordered pair for T and P to help me find the rate. So 12 equals 7e to the r times 3. Well, I'll divide both sides by 7, e to the 3r. Then I'll take the ln of both sides and bring down this power with the power rule. And so I'll have ln of 12 over 7 equals 3r. And so r would equal ln of 12 over 7 divided by 3. Okay, well, let's get a calculator and see what that amounts to for a rate. Ln of 12 divided by 7, don't forget to close those parentheses, divided by 3. I end up with r equals 0.1796655,002. Or if we're talking about the rate, we could say approximately 17.97%. That's a pretty quick growth rate. Watch out, those gnomes are busy. All right, so the next question is, how many gnomes are there after 10 years? Well, let's build our gnome population model now that we have a rate. Our gnome population model is going to be the initial 7 gnomes, and then e raised to the 0.1796655,002t. And we're asked how many gnomes will there be after 10 years. Is 10 a p or a t? 10 is a time. It's 10 years. So I'm going to plug a 10 in here. I'm looking for p of 10. 7e to the 0.1796655,002 times 10. And now it's just calculator work. I'm going to multiply that answer, that rate, times 10. And I'm going to raise e to that power. And I'm going to multiply that by 7. And I end up with, after 10 years, I have 42.206 gnomes, or approximately 42 gnomes. Please make sure on the test you give me the 3 decimal place version of this answer, not just this approximation of 42 gnomes. 42 gnomes will not be sufficient on the test. Okay, and then the last question we have here is, when will we have 100 garden gnomes? Well, is 100 a time or a number of gnomes, a population of gnomes? It's a p. So I'm going to plug in my 100 over here for population, e raised to the 0.1796655,002t. And I need to solve this equation for time. So let's go about doing that. We'll first divide by 7. And then we'll have 100 over 7 equals e to the 0.1796655,002t. Now I need to take the ln of both sides of this equation. And I can pull this down in front. Okay. It's going to be ln of 100 over 7 equals 0.1796655,002. 0.166550002t. And now I need to divide by the rate. 0.17966550002 is what I'm dividing by. And that will give me the time it takes for me to have 100 gnomes in my backyard. So the ln of 100 divided by 7, close those parentheses, and don't forget to divide by 0.17966550002. I end up with t equals 14.801 years in order to have 100 gnomes. Okay, so there's my first gnome problem. Now I have a slightly more gruesome gnome problem. When a gnome dies, it radioactively decays. A cat wanders into my garden and kills a gnome, but in true cat fashion, just killed it for the fun, never intending to actually eat it. The gnome is left to decay. The half-life of a gnome is 15 days. Half-life of gnome is 15 days. And like we did on Monday, we can use this information to build our k. We know k is going to be ln of a half over 15 days. Well, that's great. And then we're told that the gnome originally weighed 22 pounds. So let's build ourselves a gnome weight model. Q equals Q sub O e to the kt. And we'll plug in our Q sub O and we'll plug in our k. So I end up with Q equals 22 e to the ln of a half over, and what was the half-life time? It was 15 days times time. I know many of you are keen to decimalize the ln of a half divided by 5. I'll get my calculator going on that now. ln of a half divided by 15, and I get this for the rate. Q equals 22 e to the negative 0.046209812 t. And because e is raised to a negative power, we know this is exponential decay. And that makes a lot of sense since we were told that these gnomes decay radioactively. Okay, so we've got our model. We're ready to look at what the questions ask. How much of the gnome will be remaining after 3 weeks? Well, remember the half-life time was in terms of days, and 3 weeks is 21 days. So I'm going to plug a 21 into my t. 21 times that rate, e raised to that power, multiply that by the initial weight of the gnome, and I get that after 21 days, the gnome will weigh 8.336 pounds, or the remains of the gnome will weigh that much. The next question I want to look at with you is, when will there be only 5 pounds of gnome remaining? Well, we've got this gnome model, Q equals 22 e to the negative 0.046209812t. And when we're asked when will there be only 5 pounds of gnome remaining, I'm wondering, does that 5 go in here for time, or does that 5 go in there for Q? Pounds, 5 pounds remaining. Pounds isn't time, so my 5 pounds goes in over here. 22 e to the negative 0.046209812t. And now I need to solve this equation for t. I'm going to divide both sides by 22. That'll give me 5 over 22 equals e to the negative 0.046209812t. And I can hear many of you saying, take the ln, take the ln. When we take the ln of both sides, we can take this exponent and bring it down in front. So we've got the ln of 5 over 22 equals negative 0.046209812 t. Okay, so in order to get t by itself, I'm going to have to divide both sides by this rate. And what do we get for time when we do that? Well, on the left-hand side, we have ln of 5 divided by the original weight of 22. And we wanted to divide that by our rate of decay, negative 0.046209812. And so I end up with, when t equals 32.063 days, there will be 5 pounds of gnome remaining. And that's basically a review of where we've been. What I'd like to talk about now is this other model. I want to talk about a logistic model. And a logistic model, I think, is a better model for population than the PERT we've been using. It's true that populations grow continuously. There's no one day when all the women in Tucson deliver babies. It's happening all the time. But I think there's a problem with population. If I build a PERT model for population growth of Tucson, what does that imply about the population of Tucson over time? It seems that as time goes by, the population is going to get larger and larger and larger and larger. And so that makes me want to ask the question, is it in fact possible for populations to get infinitely large? And I don't just mean the population of Tucson, which can't get infinitely large, because we certainly don't have enough water for an infinite number of people here. No, I'm talking about all populations. Like, think about the bacteria in the kitchen sponge, or the bighorn sheep in the Rincon Mountains, or the number of people on the planet. All of these are populations, and I don't think it's possible for all of them to grow infinitely. So we need a new model. This isn't a model that I'm going to ask you to build equations for like we have been with exponential growth and decay. But I do need you to be familiar with the way the new model looks, and some basic things on how to, say, graph it and solve with it and answer some questions about it. Especially those of you taking more math after this class, you'll find that you need it, calculus students for sure. So let's take a look at a logistic model. A logistic model tries to be a little more realistic than our exponential growth models. Our exponential growth models are great at modeling near-term population growth, but not so good for long-term. So we need something that starts off like exponential growth, but over time recognizes that there's a carrying capacity of the environment. So our exponential growth models tend to look like big old S shapes. They start off with exponential growth, and then they flip, they go concave down, and they're still increasing, but they're increasing at a decreasing rate. So the closer you get to maximum carrying capacity of the environment, whether it's how many bacteria that sponge can hold, or how many bighorn sheep can live in our mountains, or how many people the planet can sustain, that would be the carrying capacity of the environment. And we're going to call that letter L. I noticed that a logistic model comes with another special thing. It's got two horizontal asymptotes. One is always at y equals 0. And I will say that again, always at y equals 0. We don't shift this graph up or down, always at y equals 0. And the other one is always at y equals L, the carrying capacity of the environment. Well, how am I supposed to find that L, Mr. Kukla? Well, let me give you the general equation for a logistic curve. Logistic curves can come in different equation types, but generally speaking, y equals L over 1 plus C e to the minus LKT is what we're going to see for logistic. Notice this L up here all by itself. That's our top horizontal asymptote. Whatever that number is, we're going to say y equals L is our top horizontal asymptote, and y equals 0 is our lower horizontal asymptote. So we've got two horizontal asymptotes. Okay, next. What about a y-intercept? Well, I know to find a y-intercept, I plug a 0 in for the input. The input in this problem is time. So we've got L over 1 plus C e to the, I put a 0 here. 0 times stuff is just going to be 0. E to the 0 is 1. 1 times C is C. And so I end up with L over 1 plus C. The y-intercept of a logistic curve is always at L over 1 plus C. Logistic curves have no x-intercepts, so you don't have to worry about finding them. They do have an inflection point, though, and we should say something about that. But let's graph our basic logistic curve. We've got horizontal asymptotes at y equals L and y equals 0, and we've got this S shape here, and we've got this point that we just discovered called 0, L over 1 plus C. That's our y-intercept. Now, this point is where the graph changes from concave up to concave down. Here I'm concave up, and then after that point I'm concave down. And it turns out what I can tell you is that the y value of that point is always L over 2. Well, that's kind of interesting. So how do I find this x value? Well, I can do that one of two ways. I can do it algebraically or graphically. So before we figure that out, let's actually see about doing a problem and see what we can do with that. Let me give you this logistic function. F of x equals 12 over 1 plus 2 e to the, 1 plus 2 times e to the negative 0.1x. So there's our logistic model. Now we know that this number on the top is our top horizontal asymptote, and we know that y equals 0 is our bottom horizontal asymptote. If I plug a 0 in for x, e to the 0 is 1, 1 times 2 is 2, 2 plus 1 is 3, 12 divided by 3 is 4. And so I'm a long way to graphing this. I've got y equals 12, I've got y equals 0, and I'm going to add y equals 4 when x equals 0. Okay, so there's my graph so far. And the only other point that we've talked about is this point, the inflection point, where the graph goes from concave up to concave down. And I said that happened at L over 2. Since L is 6, I'm looking at 12 over 2. I'm sorry, since L is 12, 12 over 2 will be 6. So 12 over 2. And what is that? 12 over 2 is equal to 6. Okay, and how do I find that value? Well, there's two things I can do. I can pull out my calculator, and I can graph f of x in y1, and I can graph y equals 6 in y2, and I can do second calculate intersect to find that point of intersection. But I could also do this algebraically. I could set y equals 6 equal to y equals 12 over 1 plus 2 times e to the negative 0.1x and solve algebraically. Let's take a look at doing it that way. 6 equals 12 over 1 plus 2 e to the negative 0.1x. This is the equation that I want to solve for x to find the x-coordinate of the inflection point. Well, if I multiply both sides by 1 plus 2e to the negative 0.1x, and over here by 1 plus 2e to the negative 0.1x, I can cancel these out like that. Now, I strongly encourage you, resist the temptation to distribute on the left-hand side. Instead, I recommend dividing both sides by 6. Look what happens. On the left-hand side, those 6's cancel. On the right-hand side, 12 divided by 6 is 2. So now I've got a 2 on the right-hand side of the equation. And on the left-hand side of the equation, I just have the denominator, 1 plus 2e to the negative 0.1x. Well, now this is a pretty easy equation for us to solve. We're going to subtract 1 from each side, and that'll give me 2e to the negative 0.1x equals 1. We're going to divide both sides by 2. We get e to the negative 0.1x equals 1 half. And then I'm going to take the ln of both sides, and I'm going to bring down the power with the power rule, and I'll have negative 0.1x equals the ln of a half. And so what does x equal? X equals the ln of a half divided by negative 0.1. Okay, if I decimalize that, what do I get? Ln of a half divided by negative 0.1. And I get that x equals 6.931. So my inflection point, if I go back up and label my inflection point on my graph, this point here is going to be 6.931, 6. I can find that point algebraically. I could also graph the line y equals 6 and graph my logistic function and do second calculate intersect to find that same point of intersection. Given a choice, I'm doing it on the calculator. Doing it with that algebra stuff, that takes a bit of time, and I have to be really careful. Not that we can't be careful, I just have to be. All right, well, let's take a look at 2 logistic problems now. Oh, and by the way, I know that I'm going fast. I'm going fast because I know you're at home watching this, and you can pause it and rewind it and rewatch it as often as you need. Okay, number 3. Population of cats in my gnome garden is growing according to this logistic model. So population of cats as a function of time is 84 over 1 plus 11 e to the negative 0.07t. So there's my cat population model. Okay, so what do we know about cats? Well, what's the carrying capacity of my garden for cats? What's the maximum number of cats my garden can contain? Well, remember, this number up top is the carrying capacity of the environment. So supposedly, and I really don't ever want to see this, 84 cats is my maximum cat population. Yikes. I don't want to see that at all. Okay, now, next question. What is the initial population of cats? Well, initial population is t equals 0. So I'm going to plug a t equals 0 in here. 0 times negative 0.07 is 0, and so I'll be looking at 84 over 1 plus 11 e to the 0. E to the 0 is 1. 1 times 11 is 11. 11 plus 1 is 12. 84 divided by 12, 7. My initial population was 7 cats. I hope never to see that either, initially. Okay. Next, how many cats are present after 5 weeks? Okay, so t was measured in weeks, so I'm just going to plug in t equal to 5 into my model. Now, that's going to be a little harder because 84 over 1 plus 11e to the negative 0.07 times 5 is not something I'm going to be doing without a calculator. But when I pull out my calculator, negative 0.07 times 5, I get then 84, 1 plus 11e to the negative 0.35, and e raised to that power, e raised to that power is 0.704688. So that's going to be 84, 1 plus 11 times 0.70468880897. I want to multiply that number times 11 and add 1 to it, and I end up with 84 over 8.7515689887. So if I take my 84 max and divide it by this denominator, I get that 9.598 after 5 weeks. So not a big change. After 5 weeks, I'm only up to 9.5 cats. I started with 7 cats. Any questions about this process? Okay, so that is a logistic example. Now I'd like to give one for you to try. The growing population of cats in the gnome garden has forced the gnomes to migrate to my attic. So now the population of gnomes in my attic is growing according to this logistic model, and this time the population growth is measured in days. So gnome population in my attic is represented this way: 110, 1 plus 27.3 e to the negative 0.14t. So here's my gnome population model. Okay, my first question is, A, the carrying capacity of my attic. How many gnomes can we get up there? Take a moment to think about and write down the answer to the question, how many gnomes can we fit in the attic? 5, 4, 3, 2, 1. There we go. That's the number. We can fit 110 gnomes max in the attic. Okay, next question. How many gnomes were there initially? Okay, here's our gnome population model. Use our gnome population model to find out the initial number of gnomes to 3 decimal places. Okay, well, to find this, I plugged in a 0 for t, and so I had 110 over 1 plus 27.3 e to the 0. E to the 0 is 1. 1 times 27.3 is 27.3, plus 1 is 28.3. And so when I did 110 divided by 28.3, I came up with 3.887 gnomes. Almost 4 gnomes in my attic at time equal to 0. Okay, and how about we find that inflection point? Let's find that inflection point. See, where, or when rather, when does the gnome population go from increasing at an increasing rate to increasing at a decreasing rate? What we're looking for here is when we go from increasing at an increasing rate to increasing at a decreasing rate. We're looking for that inflection point where we go from concave up to concave down. Well, we said we know the y value here is L over 2. And since our L is 110, we know the y value is 55. So at this point, my recommendation was that you take 55 and set it equal to our gnome population model, and either algebraically solve this for x, or graph 55 in y1 and the logistic model in y2, get them graphing on the same viewing window, see the point of intersection, and do second calculate intersect. So I'm going to wait a moment while you solve this problem. Either way is fine with me. It would be good to be able to solve it one way. I'm going to be doing it the graphical method. Don't forget, everything in the denominator, if you do it graphically, has to be in parentheses. Okay, if you're not ready, you might want to pause the video until you get ready. I use the calculator method to find this point of intersection, and we already know the y value here is 55, half the carrying capacity. And when I did second calculate intersect, I got 23.621 as the x-coordinate. That means after 23.5 days approximately, the population of gnomes is going to go from increasing faster and faster to increasing slower and slower. This is the moment in time when gnome population is growing fastest. All right, well, those are our logistic models for you. You should be able to do the in-class worksheet with the sub now. Remember to send your questions on the GroupMe. However, I'm probably on a plane today while you're watching this, so I don't know that I can answer them during class. But as soon as I land and have an opportunity, I'll answer any questions you have. I'm also going to try and put up a video for the exponentials on parade, which is to say I have one, but it's out of sync, so I think I'm going to try and redo it now. Okay, well, I hope you have a great Thanksgiving, and I'll see you on Monday. Take care.